Hey everybody, this is Larry. This is day 26 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Is remove duplicate letters. Didn't we do that yet? Oh, wait, no, we did not. Well, definitely did not do it yesterday, but I guess it was very similar. Given the string S, we move duplicate letter. Can read. Cat got my tongue. The question is apparently the same as this other problem in the notes. Remove duplicate letters so that every letter appear once and only once. You must make sure your result is the smallest in lexicographical order amongst all possible results. The second part may be a little bit tricky, but we'll see. That is actually a kind of an interesting problem, right? I think if you didn't have that constraint of the smallest lexicographical order, you can probably do it very quickly, right? You can just do it in basically O of 1. Wait, why did I say it like that? No. I mean, you could do it very quickly. You could just like, I said it wrong. I don't know why I said O of 1. Maybe today's a little bit weird day. But basically, one pass is what I meant to say. My apologies. Because, well, you can just remove things that you've already seen, right? And it doesn't matter which way. But of course, you have to do it. You do have to do it in the smallest lexicographical order, and so that makes it a little bit trickier, I think. Let's see. I think the idea. Obviously, if you do n squared, maybe it's a little bit easier. But I think here we have to come up with an idea, something that's an invariant, something that we can think about, to be greedy with, right? In a way. So okay. I have some ideas, to be honest, but I'm thinking through the implementation. My idea would be initially, get every letter that you have access to, right? And then, all the unique letters that you have access to, and then do it one at a time and add it in, right? For example, you want to add A first, and if you add A, well, then you have a choice, right, for B, which is either before A or after A. And of course, you always want it to be after A because I don't even know if this is the exchange argument, but you can make an exchange between the two and it's very obvious, right? And in that sense, you also want the A to be as early as possible to leave yourself the possibilities of squeezing things on later. So maybe that would be the greedy. So here, I think that's the idea that I'm going to go with. The proof may be a little bit sketchy. We might have to play around with it. But here is that one letter at a time, start with A, and then next, go with B, and the next B that comes up, and then C, right? But then now you have to add a... actually, maybe that's wrong, huh? Because it doesn't even work with this one. I was going to say if you do A and then B and then C, but then now the D is ahead. So you actually want A, C, and then D before the B. Dun, dun, dun. Actually, no. I get why I was thinking this way. The idea, okay, yeah. Sorry, if you want to think about it this way, I was just giving you an example of what not to do with greedy, right? Because as you can see, that will give you a wrong answer. Actually, I had this other thing in mind, but I somehow kind of got them confused and then fell into this silly greedy case. But the other thing is then, well, okay, so we can actually do what I just said because, like I said, if you, let's do it together if you want some visualization, right? If you start with this, and you start with A, and then you throw everything before away, then, and then you go, okay, well, let's get the B from here then. We have to get the B from here because we threw it away. And then now, that means we threw this away. We have C, but then now what happened to the D, right? Well, we have to add it from the D here, then that's already slower, or later in the lexicographical order. So that's no Gucci. So what can we do to remedy this, right? So actually, it turns out all you have to do is just keeping the invariant that in each loop, you want to make sure that every letter you want the smallest letter that does not eliminate that makes it still possible to get every letter. What I mean by that is that, or every remaining letter in any way. So for example, here you can say, okay, well, if we choose this A, what happens as the first step, or as the next letter? Well, we can still get all the, all the possible letters are A, B, C, D. We still can get A, B, C, D from here. Okay, what's the next letter? We choose a B, right? Or do we try a B? Well, a B, everything after B is not, you're only able to get C and no more D, right? So you cannot do that. All right, well, then we try a C. Okay, we can't do a C because after that, we still have D and B, which are the remaining letters. So I think that's the way that I would approach it. And because of that, if you're able to do it quickly, it shouldn't be that bad, right? Because now you only do, let's say you do everything in linear time, and you could probably do better than linear, right? Or well, it depends on what you mean by linear. But if you could do check in constant time, but no, even well, depending on how lazy you do it, I suppose. But yeah, if you do it in linear time for each character, you only do this 26 loops, right? So if you're a little bit sloppy about it, you do it like 26 times n, so then it becomes 26 square or alpha square. And of course, I'm going to pull out my calculator. That's like 676 times, okay, maybe that's 6 million, which is 6.7 million, which is maybe a little bit slow, but there are, the constants are low, and also you probably get to skip like half of it, like and choose like 26 choose 2 instead of 26 or something like that, right? Is what the complexity always work out to. So maybe that's fast enough, but you could probably be a little bit careful. But that also means that this is a possibility, right? And this is actually a technique that comes up a bit, is that once you figure out an invariant, which is that once you figure out the invariant, then you could add that to your loop and then make sure that in every step of the way, that's how you do greedy. Is that, you start with your smallest character that you can go while you're still keeping track of the remaining letters. Okay. Okay. Yeah. I'm trying to think how to do it in a quicker way. And there's some stuff about binary search. I think that's really the core of that idea. Is it going to be right? I don't know. We'll see. Let's play around with it in terms of implementation, but I think that idea should be good. So let's get started. Right. So here, maybe we just put everything in indexes, right? Right, so now indexes of the character, we'll have a list of indexes. So then now we choose, so then we have an answer, right? So while length of answer is, maybe we just have like a set of this or something like. Like all. Okay, or is it or characters or something like this? Maybe, right? Oops. So then, while this is true, we want to get the next get the smallest or earliest is probably technically more correct. The earliest character that is that allows the rest to be done, something like this. Maybe I have to rewrite the conditions a little bit differently, but that's, yeah. Okay, so then now we just start with, actually, I guess we can, I think set is ordered, but I'm always like, I always forget all the weird rules about it. But let's put this on a deck, actually, so that I can. No, not on the deck. What do I want? I want it on a set. I guess technically I wanted a sorted list, but I think a set is actually also fine. Is that true that set is always Sorry, I feel like I knew this, but I mean I could just also use sorted list because I or sorted set I suppose, but there's assert sorted set s is equal to set s. Is that always true? Okay, it is not. I thought that I don't know if I'm just remembering it from some weird place or something. That's why. No, that looks okay. Well, I mean they're just different because they're different types. But still false. Why is that? Is that because sorted is an iterator? Still false. What am I missing? They look the same. ABC, ABC, right? Why is that returning not the same? Maybe. Well, this is definitely not the same in either case. Oh, maybe I was just looking at the sec. I don't remember what I was looking at. But okay, so my theory is wrong on this. So oh well. Yeah, let's use a sorted list or sorted set. Maybe it's a little bit high powered, but you see why I want to do it this way in a little second, right? Because I just wanted to basically for C in or C, right, is what I want to do. And this goes from left to right, so then now we don't have to worry about sorting it again. And in theory, you can also do it the other way of like for character is A, B, C, D, dot, dot, dot. But the way that I did it this way, now we get to skip the letters that we don't have left or used or whatever, right? So it's slightly faster, probably nothing to really nothing to really to worry about per se, but maybe it's just a little bit nicer to do it that way. Anyway, and then now maybe something like we can even just like if this is good, then or C, we move C, enter that append C, and then again we turn to enter, right? And that should be basically the idea. Maybe we have to change this a little bit because clearly that's not no Gucci. But while this is maybe I just go I don't know, A is equal to length of or C, and then now this is less than A is prior, you know, because then now we separate these two as we change, right? So yeah, I mean this is obviously wrong because we didn't implement a good function, but I just wanted to double check that it doesn't like give me I call it compiler error. It's not really a compile. Obviously, Python is an interpret language, but like if I have a typo or whatever, and it gives me an obvious error, I just want to make sure that I do it now instead of yeah. I call it a compiler error. I mean, I also know pedantically it's not a compiler error, but it's just like me checking for compiler error is what I mean. Yeah, you could take it as you will, but I wouldn't say that in a more precise technical meaning. Just colloquially, I guess. Anyway, yeah, so here what is good, right? Think about this, right? So this is good if the first instance of this character and will the first instance of this character is going to be so we'll weight it naively to begin with. I think there's actually another way to do this that I know. But I don't know if it's worth that optimization. We could talk about it afterwards. So I'm just going to do it this way now, and then we'll talk about the optimization and see if it's needed. Then we'll actually do it. But yeah, but basically it's okay. So first index is equal to indices of C, right? Of 0. So this is the and in a greedy kind of way, we always want to take the first because our condition is that I'll allow the rest to still be alive. Then of course, yeah. Then as early the better. So then now we just have to go for x in or C if index ceases of x if bisect left of this of first, right? Okay, so this is the next index, right? So indexes of x of index, which is confusing. So if well, first of all, if this is, it has to be between these, right? If this is bigger than or equal to, and the equal to is just really for the case where c is equal to x. But if this is greater than or equal to first, then we're good. So that means that the opposite of that means that if this is if this is earlier and this is, I guess that's not possible, is it? Because in this case, then it's just 0. So everything I'm getting confused myself then. So yeah, everything. So if this exists, then that means that that means that it exists. So this is good. So that means that if we not this, then it is not good. So then we can return false. Okay. Right. Okay. Well, that's no bueno. Oh. I think I have to do additional things. I mean, I think we're fine, actually. Oh, no. I did this other idea in my head, but in that if this is good, so there are two things to do. One is that if this is good, we remove all the indexes, right? Index where it is before first. That's what I wanted to do, and this would have worked, but this is why we are able to get 0. But maybe that's a little bit computationally expensive. So we can actually, just keep track of the first overall, but maybe that's a little bit yucky. The first is 0, right? So then now, we want to do a bisect left of indexes of C of first, right? Oh yeah. Maybe the current. Basically, this now just has a current marker, and then now this does a bisect left. And then, I mean, this is fine, but now we have to update this somehow. But then we have this true false thing, so I have to kind of be a little bit careful about how I. Okay, if this is good, then I mean, you can do it inside here as well, but I guess I'll just put it here. So we do so current is equal to okay, index is equal to this, and then indexes of C of index, right? So that's going to be the next index. So then we want this to be +1 to get to the next index that we're able to look at by doing this. Something like this should be fine. Oh yeah, I forgot to keep track of did I remove it? Can this ever be possible? Actually, I thought that this would always be possible. Oh, I guess, okay, it's not that. It's at this part, right? So, no, this should also never be impossible, right? Just by definition of how, or like if everything else is right, this should always be possible. And this as well as a result. So I think I did something wrong here. C current. Let's see. So A, this is the first one. A goes to 3. Yep, that's right. And C goes to 5. Okay. Well, I mean, this is doing it wrong. It should be B. Oh, I see. Maybe, but we should break in any case. I think that's the biggest problem, or one of the problems. Okay, so yeah, so we at least fixed the case 1. It seems like 3, 4, 5, because we didn't break. So the states are probably in a weird way. I feel like it should still work, but maybe there's some like weird state that with respect to the concurrency definitely is a little bit awkward, and it's definitely wrong. I mean, it should have worked for this case, but I think it's possibly wrong, and it's definitely wrong in either case. But yeah, so here we have ABC. So this is already wrong. So we have A is, and then we have 3. We buy. Don't know how this comes about. If this is out of bounds, we return false. Right, we always want to find a thing in it, right? But it doesn't. Huh. All right, let's print something out real quick. Oh, first is it's a little bit sloppy. It should be this. This is the first index, not the first. So it should be something like first is equal to indices of C, or first index. I think I messed it up here and here. No, this one I think I got it right, but that's okay. So a silly mistake for sure. Or like I changed some stuff around and then I didn't follow it through. Okay, so now it looks good. Get rid of our print statements. Are we Gucci? I think I mean, Algo, I think we're okay. Maybe it's a little bit slow, so we'll see. But implementation wise, we'll see. So I'll give it a submit. And oh, there you go, 1274 day streak. And it actually turned out running pretty quick. What did I do before? The suffix. This is actually pretty cool. I'm not going to go over in this video. I probably have a video for that one. That's a pretty cool idea, actually. And I guess this one I did it the same way. I did it with the range 26 instead, though. But today I used a sorted set. A little bit of an optimization, though. It's a little bit slower, so it's not a good optimization. The other thing you can do, and I actually, that was what I did in the first go. I said that, you need to optimize, but you weren't able to optimize, you need to optimize because it's too slow, but we don't need it for this one, is that I would just trade time for space. And what I mean by that is that there are a couple of ways you can do it. It's just, you can think about it as a suffix, like a suffix existence thing, right? So that means that is then you pre-calculate, is there an A after the fifth character? Is there B after the fifth character? Is there C, ... for all n's? So you have alpha times n space, but then you could do all of one lookups, and you could do, and that's what I did in the other case, and you do all at once. This is going to be all of one instead of all of log n. So then, so it's a little bit faster, but apparently it doesn't really matter. So yeah. So what's the complexity here? Well, what's this loop? This loop obviously will run all of A times, where A or alpha is the size of the alphabet. So this is O of A loop. This is also an O of A loop, which is why I was a little bit scared. And the good loop is going to be, this is O of A as well. And then it's O of A of this here. But these are just log n, right? So this is O of A log n. So then now in total, as you can see, should be O of A cubed times log n, right? What is that? 26 to cube times log n. I mean, n is 10 to the 4th, so it's like, what, 15 or something? I don't know what it is. So that should be really fast. I think I just did the math wrong earlier. Well, initially I thought that, like, okay, we can do a linear scan, but turns out I was like, whatever, I'll just skip ahead and do the binary search instead of kind of teasing y'all. So yeah, so that's the complexity, and that's gonna be good. Or is this, I guess plus A for the answer, but yeah, and also plus N for the obvious reason of we have to pre-process this thing, so that's gonna be O of N. This is, I guess, technically, depends on if you're sloppy or not. Maybe this is, I actually don't know how they do it internally. So maybe this is n log n, but if you're a little bit smart, you could just put it in a set first and then sort it. So that'll be a log a or something like this instead, which I guess I didn't factor into, but that gets dominated by a cube. So yeah. And if you do it the other way, so this is time, and what is space? Space is O of n, and that's pretty much it, I think. Oh, and I guess O of a plus n due to the sorted set. So this is O of alpha plus n is space, and if you optimize it, you can optimize the log n away. So, but it becomes O of a cube plus a times n, which may or may not be faster, right? Depends, but O of a times n space for that optimization, right? And this is for calculating the optimization. Though maybe we do a little bit better. I don't know. I mean, yeah. Cool. That's all I have with this one. Let me know what you think. Like I said, the core part about this is just coming out with the invariant of what you want, and then kind of systematically look at it one by one and solving it. As long as that invariant holds, right? Because basically the invariant is that after you remove this character C, you can still construct the rest of the characters after it. Yeah, anyway, that's all I have for this one. Let me know what you think. Yeah, stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.